Hey there, Chem Squad. In today's class, we're going to look at periodic table trends. So sometimes these are just called periodic trends, but most of these we've kind of already dealt with from grade 10 onwards. Some of them we've even talked about earlier last week. But for the most part, I'm going to reintroduce to you some of these trends. There's a total of 5 of them. 4 of them we've kind of talked about before, and the 5th one is the newest one. So before we actually start, I just want to clarify that when we're looking at a periodic table, okay, if we're looking at a column on a periodic table, most scientists, most chemists would call it either a family or a group. Okay, I've gotten you to written in all the family names in the past. So most of your periodic tables will have 1A, 2A, all the way up to 8A. So if we look at family 7A, family 7A is the same thing as group 17. The only ones that don't have a family designated with an A are their transition metals. So that's why when you look at the groups actually run from 1 all the way to 18 because they include the transition metal elements. Now, when we look at a row on a periodic table, most of you guys have been looking at these rows as if they were energy levels or shells of a Bohr model. But we actually call every row on the periodic table as a period. Okay? So columns represent families or groups. Rows are represented by the word period. So if we actually start with the first periodic trend, the first periodic trend is metallic character, okay, and the second one is non-metallic character. For metallic character, metallic properties increase when you move across the periodic table from right to left. Okay, so moving from right to left like this, going from your nonmetals to your metals, of course your metallic properties will increase. If we want to see the increasing trend of nonmetallic properties, okay, then we basically start from the left side and we move towards the right side. Okay, so basically going from metals to nonmetals would of course increase the nonmetallic property. And again, this is something that you guys are very familiar with, mostly because when we taught you the differences between metals and nonmetals, okay, we focused a lot on the staircase here. Okay, the staircase itself just divides the periodic table between the metal side and the nonmetal side. Okay, so when you apply the periodic trends, nonmetal properties of course has to increase going from left to right, and metallic properties have to increase from right to left. So this is more or less a review of those two periodic trends. As we approach electronegativity and ionization energy, these were two newer concepts that were introduced to you in this unit. Electronegativity means the ability for an atom to attract electrons. So when we're looking at something like this, okay, the electronegativity of an atom increases as you approach fluorine. So that means electronegativity increases when you move from left to right across the periodic table. Electronegativity also increases when you move up a family or group. Okay, so when you move up a family or group, electronegativity will increase, but the major trend is as you approach fluorine from any direction on the periodic table. So if I start at francium, okay, francium going towards fluorine, I would see an increase in electronegativity. Okay, so that means the atoms that are close to fluorine, okay, oxygen, sulfur, chlorine, nitrogen, phosphorus, okay, bromine, they would all have high electronegativity values. The noble gases are the only exception because the noble gases tend to have an electronegativity value of 0 because they're already stable with their complete octets. So if we look at how the ionization energy trends fit in, okay, ionization energy just means how much energy is required to remove an electron. Okay, so we already know from that particular lesson that when you go down a family, ionization energy decreases. Okay, so ionization energy decreases when you move down each family. But the thing is, when you move across the periodic table from left to right, okay, again going in this direction, ionization energy actually increase. Okay. So ionization energy increases as you move from left to right, but ionization energy decreases from the top of the family to the bottom of the family. Now, the reason why ionization energy increases as it goes from left to right has a lot to do with the electronegativity. Okay. So again, let's look at fluorine. Fluorine has the highest ability for attracting electrons. So it wants to keep all the electrons that it has gathered. Ionization energy is the amount of energy that you need to remove electrons from an atom. So any atom that has a high electronegativity would require a high amount of ionization energy in order to forcibly remove those electrons away from it. So that's why ionization energy has to increase moving from left to right across the periodic table. And then finally, we come to something called atomic radii. This involves the size of an atom. Okay? Because we're actually looking at the radius of an atom. But the way that we measure atomic radii kind of goes something like this. We don't necessarily know how much space or how many orbitals are present in an atom, okay? But the one concrete thing that we can figure out is its nucleus. So if this is some kind of random atom, okay, with a nucleus, if we have another atom that is exactly the same, it would also have its own nucleus. If we can measure the distance between nuclei to nuclei, okay, let's say that this is your distance. So d is the distance between nuclei. Okay, then the radius has to be half of this. Okay, because the idea is half of this distance would mean we go from the center of the nucleus to the outer edge of the atom. Okay, so the radius r is basically d divided by 2. So when we're looking at the size of an atom, we're basically looking at the length of the radius, r. So let's look at the trend. The atomic radii increases when moving down each family. Okay? So if we're going down the family, the radius gets larger, or the atom gets larger. So if we look at lithium and sodium, you can tell that the atom itself is larger. Okay? But the thing is, when you're looking across the periodic table from left to right, the radii actually decreases. Okay? So if I were to move from left to right, the radii decreases. Okay? And the reason itself is actually pretty simple. Okay? So this is what you have to think about. When you're moving from left to right, okay, the number of energy levels in shells of electrons do not change. Okay? So, for example, if you're looking at the second row, okay, this is the second energy level. We know that there's going to be 18 electrons in this shell. Okay? So as you move across the row, what happens is the number of protons will increase. Okay? The number of electrons increases as well, but the number of electrons are still in the same energy level. Okay? So really what's happening is when you increase the number of protons, okay, the positive effect of all those protons inside the nucleus pulls on the electrons. Okay? Those electrons basically come closer to the nucleus. There's no shielding effect here. Okay? Because you're not increasing the number of inner electrons. Okay? You're doing that when you're going down the family, but when you go across, you're just adding electrons to the same shell. Okay? So there's no repulsion. Okay? There's no way of making this atom bigger. So instead, what happens is all that positive charge from all those protons, they just pull those electrons closer towards the nucleus, and therefore decreasing its size. So that's why when you look at this little graphic here, going from lithium to fluorine, fluorine is a smaller atom compared to lithium. Okay? Chlorine is slightly bigger than fluorine, but it's still smaller than sodium. So these two trends are kind of important in determining the size of an atom. Okay? So hopefully this lesson here is pretty straightforward. Okay? If you want to see all of these trends on one periodic table, if you just Google search periodic trends, you'll likely find images like these, okay, where they identify all of the trends on a single periodic table. So something like this might be useful for some of you guys who are visual learners. Okay, so that's all I have for today. I hope this video has helped you a little bit in terms of understanding periodic trends. See you guys soon.